So, picture this. Imagine the ground beneath your feet suddenly, violently betraying you. The sea rose boiling in the harbor. 30,000 inhabitants of both sexes and all ages were crushed to death under the ruins. Those are the actual words of the philosopher Voltaire in his famous book Candide. He was describing the absolute nightmare that was the 1755 earthquake in Lisbon, Portugal. I mean, this was a cataclysm so massive, it literally shook chandeliers over in the United States and rattled buildings all the way across Europe. It's just a visceral reminder of the immense, totally uncontrollable power of nature that we're exploring today.
Welcome to The Explainer. Today we're going way deep under the Earth's crust to basically demystify the terrifying mechanics of earthquakes. We're going to look at the science, the history, and the incredibly complex systems we use to try and understand the very heartbeat of our planet. It's a fascinating journey, so let's just get right into it.
Okay, let's dive right into this. Because, tracking a threat that can literally strike anywhere on the globe, it requires a massive, unified worldwide effort. We're talking about an interconnected web of international agencies keeping watch 24/7. You've got the EMSC covering Europe and the Med, using crowdsourced eyewitness data. Then there's AFAD in Turkey, NICE out in India advancing seismic safety, and of course the USGS in the United States. They're constantly monitoring, collecting, and sharing data just to keep humanity informed.
But what happens when all that data just goes dark? Even our most critical databases, like the NOAA or FEMA earthquake guides, are totally susceptible to server crashes and those dreaded Error 404 or access denied outages. And honestly, it's a pretty subtle but terrifying reminder of what happens when our continuous digital access to global disaster info gets interrupted. We rely so heavily on these fragile digital lifelines to prep for the worst. To really wrap our heads around why this global tracking network is absolutely critical for our survival, we kind of need to look back at history.
Which brings us to Section 1, History's Most Destructive Shocks.
Let's compare two massive historical events here. Back in the winter of 1811 and 1812, the New Madrid earthquakes in Missouri sent shocks across 2 million square miles. That's basically from Canada all the way down to the Gulf of Mexico. But because the area was pretty sparsely populated back then, casualties were incredibly low. Now contrast that with the 1906 San Francisco earthquake. That quake and the terrible fires that came right after it killed nearly 700 people and left a major city in total ruins. So the destructiveness of an earthquake relies heavily on human geography. Honestly, if the New Madrid quake happened today, the central Mississippi Valley would be utterly devastated.
And this brilliantly illustrates the sheer, raw force of that 1906 event. I mean, look at that. The ground literally warped railroad tracks into iron zigzags. No way a train is getting over that. And it turns out, most of these catastrophic events occur in one highly specific geographic area. Notice the yellow zone highlighting the notorious Pacific Ring of Fire. Over 500,000 people living in this circum-Pacific belt have tragically lost their lives to earthquakes.
But here's the thing. The shaking itself isn't always the main culprit. If we shift over to the Great Alaska Earthquake of 1964, we see devastated tracks and completely slumped bluffs. Often, it's the secondary effects, like massive landslides and towering tsunamis or seismic sea waves, that cause way more destruction than the shocks themselves. Entire residential developments, like Turnagain Heights in Anchorage, were simply swallowed up as the unstable Earth just broke apart and slumped northward.
Yet, despite releasing perhaps twice the energy of that devastating San Francisco quake, and featuring ground motion so incredibly violent that the tops of trees were literally snapped right off in half, do you know how many people actually died in the 1964 Alaska quake? 114. Just 114 people. And the only reason that number wasn't in the tens of thousands is simply because, again, the area was so sparsely populated at the time. So, okay, we've seen the human history and the surface-level destruction, but what is actually happening down below?
Let's find out in Section 2, Anatomy of an Earthquake. We're looking under the hood of the planet.
Okay, so it all starts with a fault. Basically, that's a fracture in the Earth's crust where two blocks have slipped with respect to each other. Deep-seated forces are constantly pushing against these crustal segments. The crust bends, stress builds up immensely over time, and, well, when that stress finally exceeds the actual strength of the rocks, they break. They literally snap into a new position. And it's that violent snapping that releases the catastrophic energy we feel up here on the surface.
Now, what's really interesting about this is that there are a few different ways that deep snap can happen. On the one hand, you have a strike-slip fault, where the crustal blocks move horizontally past each other. California's famous San Andreas Fault is a prime textbook example of this. Contrast that with a dip-slip fault, where the movement is actually vertical, so one block is moving upward while the other drops downward.
Now you hear these next two terms on the news all the time, right? And they are constantly getting confused. The focus is the actual region deep underground where the earthquake's energy originates. This can be relatively shallow, or get this, it can be a staggering 440 miles deep inside the Earth. The epicenter, on the other hand, is simply the geographic coordinate right on the Earth's surface directly, vertically above that deep focus.
Let's move along and see how this builds. When that snap happens way deep down at the focus, the energy radiates outward in the form of seismic waves. They travel straight up through the crust to hit the epicenter, and then they spread out all across the Earth's surface.
And those radiating seismic waves, they actually come in a few different flavors. The body waves that travel through the Earth are split into P waves and S waves. So P waves are your primary waves, they're compressional, pushing material directly ahead of them, and they travel incredibly fast, arriving first. S waves are secondary, so they arrive a bit later. These secondary waves are shear or transverse waves, and they are so incredibly powerful, they literally cause the entire planet to quiver or ring like a massive bell or a tuning fork. It's wild to think about.
To follow those waves in action, you can see how the fast P waves manage to travel straight through the Earth's molten core. But the slower S waves, they don't travel as rapidly. And because they displace material at right angles to their path, they actually cannot pass through the molten core at all. By tracking exactly which waves arrive where and when, scientists can effectively map the hidden interior of our world. Which, of course, brings us to a really critical question. How do scientists actually quantify this terrifying Earth-ringing energy?
Let's talk about that in Section 3, Measuring the Impact, how we quantify the energy. The primary tool for all of this is the seismograph. Basically, it's an incredibly sensitive instrument that detects, records, and measures the vibrations coming from the ground. By analyzing the varying amplitudes of the delicate zigzag lines it produces, which is called a seismogram, scientists can determine the exact time of the quake, pinpoint the epicenter, calculate that deep focal depth, and even estimate the total amount of energy released.
Now, we typically hear about two different scales when assessing a quake. The famous Richter scale is a cold, hard, mathematical measure of the seismic wave's amplitude. It's a logarithmic scale, meaning a magnitude 7 quake is literally 10 times larger in ground motion than a magnitude 6. So contrast that objective math with the modified Mercalli scale. This one is a subjective scale, ranging from Roman numeral I to 12, and it measures the actual physical damage and intensity felt by humans in a specific location.
So the crucial point here is, magnitude alone does not equal destruction. Just think about the Government Hill Elementary School, which was utterly destroyed in the 1964 Alaska quake. Surface destruction relies heavily on local geology. The town of Whittier, for example, was closer to the epicenter, but was built on firm granite, so it suffered very little direct shaking damage. Anchorage was much farther away, but areas built on unstable, unconsolidated clay suffered catastrophic failure. Honestly, where you build is just as important as how big the quake is. So we understand the history, we know the mechanics, and we can measure the impact. But what about the future?
That leads us to Section 4, the frontier of prediction, forecasting the great unknown.
Long-term prediction involves looking at what we call seismic gaps and historical fault cycles. And scientists actually found an incredible real-world laboratory for this in Parkfield, California. Records dating all the way back to 1857 showed that moderate-sized earthquakes recurred on this one specific section of the San Andreas Fault every 21 to 22 years on average. The seismic events were just remarkably similar. So based on this historical cycle, scientists made a really bold forecast, one endorsed by the National Earthquake Prediction Evaluation Council, that the next moderate quake would hit in 1988, give or take 5 years. It provided this completely unique chance to set up instruments and try to catch short-term precursor warnings right in the act.
We have come so incredibly far from the days of the 1755 Lisbon quake, where people literally thought rushed air from underground caverns was causing the shaking. Today, we have global tracking networks mapping the heartbeat of the Earth in real time. We understand the faults, the deep focuses, and the sheer power of the waves ringing our planet like a bell. Yet despite all our scientific progress and dedicated research into fault cycles, short-term prediction remains an incredibly challenging hurdle. So the ultimate question remains, will we ever be able to predict the exact moment the next big one strikes before the ground opens up? It's a mystery the Earth still holds very close to its core. Thanks for joining me on this explainer, and keep staying curious.